For question 68, please read the following problem. Electron affinity is the measure of the energy released when an electron is added to an atom, molecule, or ion. The larger the electron affinity, the easier it is to add an electron to that species. The molecular orbital diagram of beryllium molecule is represented below. With the information provided by the molecular orbital diagram, you can determine that the valence shell electron configuration of the beryllium molecule is sigma 2s squared, sigma star 2s squared. The molecular orbital diagram of a fluorine molecule is represented below. With the information provided by the molecular orbital diagram for the fluorine molecule, the valence shell electron configuration can be determined to be sigma 2pz squared, pi 2px squared, pi 2py squared, pi star 2px squared, pi star 2py squared, sigma star 2bz to the 0 power. The molecular orbital diagram of boron ion is represented below. With the information provided by the molecular orbital diagram of the boron ion, you can determine the valence shell electron configuration to be pi 2px to the first, pi 2py to the 0 power, sigma 2bz to the 0 power, pi star 2px to the 0 power, pi star 2py to the 0 power, sigma star 2pz to the 0 power. The molecular orbital diagram of carbon ion is represented below. With the information provided by the molecular orbital diagram of the carbon ion, it can be determined that the valence shell electron configuration will be pi 2px squared, pi 2py to the first, sigma 2pz to the 0 power, pi star 2px to the 0 power, pi star 2py to the 0 power, sigma star 2bz to the 0 power. Electron affinity is the measure of the energy released when an electron is added to an atom, molecule, or ion. The larger the electron affinity, the easier it is to add an electron to that species. From the molecular orbital diagram, it's clear that the electron affinity of the beryllium molecule will be the highest because large amounts of energy will be released when an extra electron is added to it. In the beryllium molecule, all the molecular orbitals are fully occupied by electrons, and no vacant molecular orbitals are present to accept the extra electron, and this is not seen in any of the other cases. In the fluorine molecule, the added electron enters an anti-bonding orbital, and in the carbon ion, it enters an orbital that contains another electron. The positive charge of the boron ion increases its electron affinity relative to the beryllium molecule.